and I'm going back home to bed. All right, so we're going to continue looking at these solubility equilibrium initially, and we started looking at something like the common ion effect, which we can solve solubilities. There's a lot of other things that we do with solubilities too. Sometimes we want to look at precipitation reactions and find out things like when will the precipitation start. We use this, we're going to learn about in the next few slides, in things like separations. Separate one cation for the other. Here's an example where you're adding chromate to a system. So that's one of those polyatomic ions you don't talk about that much, but chromate, CrO42 minus, and I want to know what concentration is required to reduce the silver in the solution down to 9 times 10 to the minus 7th molar by precipitation. So you're starting with something higher than that. Doesn't matter how much higher than that, but you're going to use precipitation to remove a particular metal. And that's a common way that we approach metal analysis or look at separations, especially environmental problems. I had a student that graduated about 7 years ago, and he applied for a job at a firm in Tulsa, and they had a tank that had, I think of the metals, it had calcium and zinc in a tank. And it wasn't a regular sized tank, it was 1 million gallons. It was a storage facility for environmental contaminant, and they had to figure out how to get the calcium, which is a harmless thing, out of it, and the zinc from the two. And he had called me on the phone and said, well, how could we possibly do this? And so we got to approach it by precipitation with that kind of volume. And he worked out the math, and he called and checked it to me, and this company asked him for this for a job interview. They didn't really have an on-site chemist, per se, that was had a bachelor's level. They had some people who had some scientific knowledge, but he went and did the interview, proposed to do the separation by precipitation, and he got the job solely based on being able to do this problem. So I thought that was a neat real-world application of it. But 1 million gallons, you gotta think, that's a big tank of liquid. I don't know how they acquired that much waste, but somehow they did. Okay, so here's the problem. I want to, I've got this initial concentration of silver, and I want to take it down to a final concentration. All right, so I've got silver initially, so this is my initial, and I want to take it down to this level of silver. This is going to be my final. So I just got to identify where I'm at. Now, the way that I'm going to do this is going to be with the precipitation. So I'm going to add silver to the chromate ion to produce the silver chromate solid. So that's going to precipitate and fall out of solution. But the thing I have to realize, what governs how far I go with this is simply the solubility of the silver. Okay, so I'm going to end up solving for this for the solubility problem. It's a slightly soluble compound. Okay, now it's not given to me on the table, or on my KSP, it's not given to me, so I've got to go to my handy dandy table, and I got to find out what the KSP is. So UB, and this is last year's test question. Get an idea where I see something like this. So I go to my solubility products, and I'm going to go find the chromate ligand, and I find silver, and I find that it's 1.2 times 10 to the minus 12. So KSP is equal to 1.2 times 10 to the minus 12. And I don't even know if this is going to be feasible to do, but we're going to find out. Okay, so KSP is equal to the concentration of the silver squared times the concentration of the chromate ion. All right, so what we're going to do is solve this to find out how much silver is needed. I want to know how much silver concentration is required to get the chromate down to this level. So it simply becomes a rearrangement and a plugging in equations. So let's do that. So the concentration of silver that's going to be required. So I'm just going to solve it with a square first. Is equal to KSP divided by the concentration of chromate. I'm isolating the silver. All right, but the silver is squared, so I want to get rid of the square. So I'm going to take the square root of both sides. So that gives me the concentration of the silver. That's what I'm looking for. So now it's just a matter of plugging in some numbers. So I've got KSP is 1.2 times 10 to the minus 12. The concentration of the silver of the I'm going backwards. I'm going after the wrong ion. Sorry, that's the mez. All right, so we got to backtrack a little bit. I'm trying to precipitate out silver. It's chromate. I'm going precipitating out the wrong ion. So just changes this bottom step. Try that again. Okay. So I got my white arrow on the wrong place. So I'm looking for the concentration of silver taken to that level, and I want to know how much chromate it's going to take to do it. Let's try that one. Okay, same thing. I'm going to rearrange for the concentration of the chromate. Is equal to the concentration of the silver divided into KSP. All right, and you got to remember to square the silver. Don't lose that. In my mind, it looks like that's a big number. Let's see what we get.
So it's the same KSP.
It's the same KSP. So this solubility equilibrium is going to stand the same as the design you're chasing. Okay, so that part doesn't change. All right, so the initial concentration of the silver doesn't matter, but we need to put the final in. So 9 times 10 to the minus 7th, and we've got to square it. If I do the math on that, what do you get?
Times 10 to the 6.
Sounds too big.
Yeah, 1.48.
Did you square this?
Oh, no.
I got 1.48 times 6.
What did you get? I just got 1.48. I got 1.42.
Okay, I think it should be somewhere around the 1 to 10 range, because when you square this number, that's going to be around 10 to the minus 13th on the bottom or something like that. Okay, so can you do it? Yeah, sure. You can make up a silver solution, silver nitrate solution, easily up to 5 molar. Now, there'd be an expensive solution because silver is a precious metal, but it's something you can certainly do.
Can you recover your solution?
Well, when you recover it, your silver, you'd recover it as the chromate. So chromate's usually considered, chromate, I can't get that in my head. So what we're adding here is the chromate. So could you recover the silver? Yeah, this may be a way that you do it. You could actually put the silver in there and then oxidize that chromate out to another form. I mean, that's one of the things in where silver is considered a more precious metal. It's still considered a precious metal, but its cost is trivial compared to that of gold and platinum. But still, like in photographic development, used to do 35 millimeter film, all these plating baths were full of silver. So you have to figure out a precipitation method to try to recover the silver, and you reduce it down into a way that would give you the silver metal back out of it. But that's feasible. And that concentration is not unheard of. 1 molar, so it's a high concentration solution, but it's not anything like, if you got something that was hundreds of molar, that's not going to work. Because remember, water is 55 molar. It's about as high as you're going to make a solution of.
And the KSP value we plugged in for this is for the silver.
The KSP value is not for the silver, it's for the combination.
Combination. Oh,
Yeah. So the KSP is for,
that whole, okay.
that all goes together for the KSP.
Okay. Why did we use that one? It's the top.
Well, the top equation's what we're doing to cause the precipitate. So this is what's going to cause the concentration of the silver to reduce as that reaction goes forward.
Okay.
But we have to realize we continue to add to a point that's governed by the solubility equilibrium.
Okay.
Yeah, because it's always, some of it's going to, even though we're forming this, some of it's going to go back into solution.
Yeah, it's just that.
Yeah, don't.
The typo will describe why some people got different answers. In the question, it asked 9.00 times or negative, and the written part it says negative 9 times 10. So
Well, that's just a dash on there, so that's where I hit it with my finger. So why could that not be negative?
We're gonna have negative.
Negative can't have a negative concentration. Okay. Concentrations can go very low, but they can never be negative. So that's a mental check you can do. If you ever come out with a negative concentration on solution, you've done something. Just a way to check that. Okay. So here's you a common ion effect problem. And this essentially is a common ion effect problem. It's just a different way of asking it. So on this one, I've got silver C2O4, that's the oxalate ion. And I've got a saturated solution of it. And it contains another source of silver from silver nitrate, which is freely soluble. And the KSP for the silver oxalate is 3.5 times 10 to the minus 11. Now you'll notice, I'll let you phone a friend on this one.
So, like we did yesterday.
Okay.
Just not Wednesday.
So y'all can talk about it. You got 3 minutes to give me an answer.
Okay.
Yeah, that's where we start.
I'm gonna say.
Start, Mark? Where did you start?
So you're looking at the-
concentration of silver squared, right?
exam
Times concentration of
Yeah.
C2O4. Yes. Yeah. Which one is plus squared.
Mhm.
Which one is all for them? Silver. Yourself for silver?
This isn't the same.
You don't think so?
No, this is like from Wednesday.
Yeah, like we did the other day.
Yeah.
Am I wrong?
Honestly, my calculator, so I can't really. But I think it's just like this. Yeah. Okay, so it was
We got two different. No, one. Silver, nitrogen. That one has got.
gives you.
Oh, God, no.
11.
Check out. Yeah. So you're dropping out your 2S, right? Is that what we're doing?
Got a minute?
What if none of us are here?
Guess we'll all learn how to do it together.
I lost my calculator.
Yeah, I'll go with it.
Okay,
Where'd you?
Just to get something there.
we got an answer. We got one that's up there.
Did you choose D?
Doesn't mean it's right, so.
What did y'all pick?
B.
B. B.
That's what I got. It was the one I could get. I don't know if I wouldn't go on my math. I'm that serious. I couldn't add 22 and 11 while ago. So.
Right there.
What do you got?
20 seconds.
Oh, man, I went the other way.
Yeah, no, that's right.
Maybe.
D.
Maybe.
Yeah, I got B.
Yeah, okay, yeah.
It's like probably says that I did.
Well, we are working this out, right?
good sign.
We are fixing to work this out, yeah.
Right?
Yeah. We have 12 of us. Yeah, we're 12 men. All right, let's see here. Boy, you all wrote with what somebody said.
Doesn't mean it's
I hope
right.
you have faith in somebody.
No.
Okay, so the thing that's soluble, you want to calculate the solubility of is this guy. All right, so this is your slightly insoluble compound. Slightly soluble compound. It's silver oxalate. It's going to dissociate into 2 silver cations plus the oxalate ion. All right. Now I tell you on this system that you've got silver nitrate, and I expect you to know from the solubility rules that silver nitrate is a freely soluble cation. So what this becomes is a common ion effect. Since the concentration of the silver nitrate was 0.01 molar, and it's a 1-to-1 stoichiometry, that means the concentration of the co-ion is 0.01, which means this concentration is 0.01. Okay, so now I need to define my solubility relationships. If this is solubility, this would dissociate to be 2 times the solubility, and this would be solubility. All right, now if I think about what's the total chromate, or the total silver, it's what comes from the solubility plus the 0.001. And I showed you from the previous problems, the common ion is the thing that predominates, so that term's going to fall out. So now when I write my KSP expression, I'll just write it in this color. KSP is equal to the concentration of the silver squared times the concentration of the oxalate ion. Okay, but I know that the silver concentration is 0.01. The square doesn't go away. Times the concentration of the oxalate ion, we said that's solubility. So that's equal to KSP. So solubility equals to KSP divided by 0.01 squared. So KSP is 10 to the minus 11. 0.01 squared is 10 to the minus 4. Divide that in, that's going to be 3.5 times 10 to the minus 7. Woohoo!
I got there. I multiplied so divided, so I went with first number up there.
Okay. A problem like this, which highly probable on the exam. You got to figure out how to set it up. What is the co-ion? At this level, I'm not going to say using the common ion effect. That's if I were giving this question to my freshman chem class when we talk about equilibria, I would say that. Account for the solubility using the common ion effect. But here, you got to recognize What's what? Question that.
You cross out 2s, but you still carry through silver squared. So what's the significance?
Well, it didn't disappear down here.
Did.
In the equilibrium constant expression, it doesn't matter where the silver comes from the solubility or from the co-ion, that this squared term didn't go anywhere. So this term is independent of the concentration or the source of the silver.
Okay.
So it's still going to always be there. So whatever power your stoichiometry is that follows down into your KSP expressions, it never goes away, regardless if the co-ion comes from somewhere else or the common ion.
So the significance would be in a KSP problem? No. Yes.
Yes. I mean, this is a KSP problem. Okay. But I'll tell you, the significance is every equilibria that we do.
Okay.
So we're starting with these. We're going to talk about all those other types of equilibrias next, but we're hammering this one down. All right. Okay. Let's go on the next one. So now I want to do kind of what we started doing with the previous problems. I want to do separations. So hopefully you watched the videos. And again, I encourage you to have read the textbook, at minimum read over the notes before you come to class, and at the absolute minimum to spend the 45 minutes or whatever it would take, 30 minutes to watch a couple of videos preceding. So whenever you're doing a separation of a mixture of metal cations, most commonly, there are a few anions that you could use to separate, and I've done some things like that. A lot of times you want to get things like perchlorate out of a solution, so you precipitate it out. The problem is perchlorates are very soluble, so what you end up doing is precipitating everything else out and leaving the perchlorates, right? Sometimes you want to get phosphates out of the solution, and phosphates you can precipitate pretty easily. What we have to do is find two species that have a different KSP value. What is significantly different? Well, you're looking at KSP values typically are these small numbers. So if KSP1 is different from KSP2 by 3 orders of magnitude, by 10 to the third, you've got a pretty good chance of getting a good separation. So that would mean when I say that, you've got something that's 10 to the minus 12 and something that's 10 to the minus 15. You can get a pretty good separation. That the closer they are, the less you're going to be able to precipitate out of the least soluble species before you start to have co-precipitation. So the way that we approach these problems is we find out how much of the ion is necessary for the least soluble species, all right, to take it down to the desired concentration. And to find out if it's feasible, you have to find out if the more soluble species will begin to precipitate at the concentration you wish to get the co-ion to. I know that looks like a mumbled mess of words. You just got to look at these types of problems. All right. I went through this one on the notes. I'm just going to describe the problem, and I'm going to, since I've worked over it, we'll go back or you can go back and watch the video. I'm going to work ones that I get to write out completely. But on this one, I used a criteria of 1 times 10 to the minus 6 for a quantitative removal. So I have a solution that has barium in it and it has silver in it, both at 40 millimolar. And I want to know if I can use sulfate to take one of them down to 1 times 10 to the minus 6. That's what we're trying to accomplish in this problem. Because you precipitate out one of them selectively. Well, if I look at the KSP values in the back of the book, the barium sulfate is the one that's least soluble because it's 10 to the minus 10. The silver sulfate is the most soluble. So the approach I would use would be to find out how much sulfate is required to reduce the barium down to that level that I want to take it to, this 1 times 10 to the minus 6. Right? So then I solve for set the equilibrium constant up. knowing I want to find out how much sulfate's required to take this one to the 10 to the minus 6. I rearrange that salt for that, find that that takes a sulfate of 1.1 times 10 to the minus 4th. I plug it in and to see if that would cause the silver to start precipitating. So the silver or the sulfate concentration, given the initial concentration of the silver, is 0.1. So this tells me that you've got to take, with this original concentration of silver, the sulfate's got to be up all the way at 10 millimolar, 0.01, before it starts to precipitate out. Here I only have to take the sulfate out to 1.1 times 10 to the minus 4th. So I probably could have changed this to 1 times 10 to the minus 8th. And this still would have been effective to separate those two. So whenever you have something that's, here in this case, separated 5 orders of magnitude, you can do a great separation of the two. And this is a real world application of how you separate out metal cations from one another. All right, so here's a test question that I gave a couple years ago, so I want to work through this one completely. I've got a solution that contains an initial concentration of lanthanum 3+. It's not a cation we use much in the lab, but it certainly has its applications in the real world. This is its original concentration. So think about this as the initial. Right? I want to know how much oxalate I would have to add. And the oxalate ion, that's not one that you maybe talked about much in other classes, but we use it all the time in analytical because it has a tendency to bind metals strongly. It's 2 carboxylate groups back to back. And if you put the protons on it, that's oxalic acid. Right? But it's a common ion used to bind to metals in analytical chemistry. So what I want to do is I want to remove 99.99% of the lanthanum by precipitation. Okay, so the thing that I'm going to do is I'm going to take and realize that lanthanum 3+ is going to bind with the oxalate 2- to form lanthanum oxalate. What ratio would they go together? Okay, so lanthanum 3+, it's going to be 2 of those. It's going to be 3 of the oxalates to form that solid that's going to precipitate out. So I've got to realize that this is a 2, this is a 3. Okay, the initial concentration of the lanthanum is 1.25 times 10 to the minus 3rd. I like scientific notation. Now, if I want to get rid of 99.99% of it, how much is remaining? Okay. 0.01% remains. So that means my final concentration of the lanthanum, 3+, is equal to the original concentration times 0.001%. So convert 0.01% into a decimal question. That's 1 times 10 to the minus 4th. So 1 times 10 to the minus 4th times its original concentration. If I did my math right in my head, it's 1.25 times 10 to the minus 7th molar. Let me check my math.
That's the same. So that's the same as it.
7th, sorry. I don't know where 4th came from.
Oh, that's 3.
Yeah,
Okay.
yeah, this is a 3.
Okay. Yeah, that's right.
So if you took this number times 0.0001, you get 1.25 times 10 to the minus 7th. Okay. So this is going to be my final concentration where my system's going to end up at. So what I need to find out is how much of the oxalate ion I have to add to reduce it down to this level. Okay, so how much of it's going to stay in solution is going to be based on the solubility of this guy. 2.4, side. Alright. So I've got solubility of the parent compound, 2 times solubility, 3 times solubility. And the KSP expression for that is going to be the concentration of the lanthanum squared times the concentration of the oxalate ion cubed. I'm going to plug in for, well, what do I need to plug in for? Well, what do I know in it? I know that the lanthanum concentration needs to go down to this value. All right, so the lanthanum concentration is going to be 1.25 times 10 to the minus 7th molar. And I know that what I'm looking for is the oxalate concentration times the oxalate concentration. And just the same way as we did on the other one, even though we're looking for the concentration, that cube power doesn't go anywhere, so it's that cube. So now it's just a math rearrangement. The concentration of the oxalate is equal to KSP, and KSP, we don't have KSP. There we go. Gotta find a table. So, lanthanum oxalate, not very soluble. Ten to the minus 25th. Tiny number. Okay, so it equals KSP. 1.0 times 10 to the minus 25th divided by, all right, the final concentration, 1.25 times 10 to the minus 7th. In the same way, this was cubed here. That means it's cubed here. How did I get rid of something cubed? Take the cube root of it on both sides. So I'm going to take the cube root of this guy and the cube root of this guy. And that's going to equal the concentration of the oxalate. So KSP divided by the final concentration. That's
Just square that. Well,
say again.
1.25. Just square that.
Square it.
Yeah.
I don't think so.
Yeah, it's just fine.
That's fine. I just want to know for sure. Because the lanthanum is squared. So do we square that concentration as well?
I think so. It's stoichiometric ratio.
Yeah, you did.
Do
Okay.
you square it?
Yes, you did. Good question. If we had to square it in all the other ones, we can't neglect it here, which I did. All right, we're going to backtrack.
Good 0.
Okay, so you're absolutely right. This concentration's squared. That one's cubed. So now we're going to rearrange this guy. So we've got KSP divided by the concentration of the, I'm just going to abbreviate it so I get to the point where I need it, squared. All right, and now that says that the oxalate ion is equal to the cube root KSP, which was 1 times 10 to the minus 25th divided by our 1.25 times 10 to the minus 7th. Squared. So what, something to the minus the That sounds right. Fourth to fifth. Yeah, remember, take the cube root of it. So you got a cube root there.
I got 26%.
All right. Question.
Is there ever gonna be a time where we find a KSP value where, for like the first equation you wrote up there? So it'd be 1 over concentrations of stuff. We incorporate that in the question,
Where I asked you to calculate KST?
just like in these examples here.
Well, in these examples, KST has always been given. But if you look at the old test questions, absolutely. If we can set up,
I'm just confused to which equation to use lately. So
well, all of these, every example we've done are the KST expression. So if I give you the concentration of the ions that are in solution, if I said a saturated solutions contains X amount of lanthanum and X amount of oxalate, absolutely I'd expect you to be able to calculate the value of KST. That's the way we find out what KST is. We saturate a solution and find the concentration of those ions. Okay? And if you change the metal or the non-metal, KST changes. Now, the other thing I told you is that KSTs are thermodynamic values. If you change temperature, KST changes. So we try to do everything at a fixed temperature. And it's critically important when you get into labs that do important calculations. They have very, very stringent environmental conditions. Usually there's a double door, so there's a heat exchanger that happens. You have to go through one door, get buzzed in, and the temperature has to equilibrate in that room before it'll buzz you in another room, because it's important in the room where the chemistry is going on. There's not changes that occur that cause these equilibriums to shift. And they also have continuous airflow. And we have a room downstairs that where the instrument room is with the IR. Its problem is that in that small room, which is smaller than this classroom, square footage wise, there is a 10-ton air conditioner hooked to it, which is usually the size of air conditioner you would have on a 6,000 square foot house, multi-level home. Huge house. It will drop temperature of that room 10 degrees in 2 minutes. But it plays havoc on the chemistry that's going on. It's the wrong type of unit. It needs to be something that was running continuously. Even our electronic instruments respond to that. And when we're doing measurements that count, we pretty much have to turn the air conditioning system on. It's an environmental concern that's something you have to think about. Okay, here's another one. So, and I'm going to try to get through this one before class is over. So you've got a solution that contains silver and barium. What makes this one slightly more challenging than the previous one we looked at is they're at different concentrations. All right, and I want to know, is it feasible to separate out 99% of either cation using a chromate precipitation? So the first thing I'm going to do is look up what are the solubilities, the KSPs. All right, so I'm going to run to my periodic table, or my table, handy dandy table in the back of the book, and go to chromates, and barium chromate. KSP value is 2.1 times 10 to the minus 10th. And if I find silvers, those are pretty close. Silver's KSP, and both of these are KSPs. KSPs. It's 1.2 times 10 to the minus 12. Yep. Okay, so now if I just looked at the values and I'd say, ooh, that's going to be tough to do because they're so close to each other. What makes them a little bit different from one another? Well, the concentrations are different. Also, they've got different stoichiometries. One's a 1-to-1, the other one's a 1-to-2. This is a really tricky problem. Okay, so let's look at the solubilities we've got. So I've got barium chromate. Solid would dissociate into the barium 2+ cation and the chromate 2-. And the KSP for that one, which was 2.1 times 10 to the minus 10th, is equal to the concentration of the barium times the concentration of the chromate. All right, let's look at the other one. The silver chromate solid would dissociate into 2 silver cations plus the chromate. Its KSP expression is 1.2 times 10 to the minus 10th, and it's the concentration of the silver squared times the concentration of the chromate. All right, first question I have for you is we know the original concentration of each species. So the original concentration of the barium is 0.01. The original concentration of the silver has got another 0 in it. It's only 1 millimolar. Okay, which one's more soluble?
Bear.
Judging by the look on your face, no. There's the science.
Okay, so the reason if you solve for KSP, if it's a 1-to-2 or 1-to-1, it's solubility the KSP squared. But when it's a 1-to-2, KSP is equal to 4 times the solubility cubed. And I think if you plug the numbers in, you're going to find that the silver is going to be more soluble. Okay, so that's part of what makes this problem a little trickier. All right, this was, I think, a bonus problem. Okay, so I'm wanting to challenge you on it. All right, so let's see where we're going to get. So y'all solve that. Y'all tell me the numbers. If we just solve for solubility, tell me what the solubility would be for each. Don't worry about how much is there originally. Let's verify to ourselves that it's really the least soluble.
Substitute for estrogen.
Yeah, so just take in, for the barium, just take the square root of KSP, which is something to the minus 5th. So this one's solubility would be something to the minus 5th. And then take that one, divide it by 4, then take the cube root of it. And I see it as something to the minus 4th, unless I made a math error. Okay, so I think the silver is actually more
They're
soluble.
both power of -5.
Okay, so which one is the winner then?
I think the barium's lower, I think.
Okay, what's the actual number, then? What's the square root of this guy?
That is 1.45 times 10 to the -5. And the other
1.4.
one is 6.69 times 10 to the -5.
Okay, it's in the minus 5th. Okay, so the one that's the most soluble is the barium. But it is 10 times higher concentration than the silver. So I think the barium, in this case, the barium is going to precipitate out first. Wow, what a challenging problem for y'all to turn in for a grade as a homework problem. All right, I'm not going to do that to you. So I'll finish that problem. We'll finish this problem in class on Monday. We're out of time today. This is going to be a problem where you have to make some assumptions, and then you're going to have to check those assumptions. This is a critical thinking problem. All right, have a good weekend. I'll get lab posted at some point today. I hope. The computer works from the hospital. Oh, one clicker question. That's no fun.
No, it helps our grade out.
But only because we all got it right.